So now I want to skip ahead from section 1 of the chapter that introduces capacitance to section 3, and then we'll get back to section 2 in a little bit. But section 3 is about capacitors in series or parallel. In order to connect up capacitors in series and parallel, we've got to connect them into a circuit. So to do that, we need to explain how to read a circuit diagram. So the first thing we're going to do in terms of reading the circuit diagram, because your book introduces circuit diagrams in this chapter, is that symbol right there is our power supply. So the power supply here, the symbol's like that, and we have a plus and we have a minus on it. So the big side is a positive, the negative side is the minus. So we normally define electric current as going from plus to minus. So we know it's electrons that are moving in the other direction, but we define electric current to be plus to minus. And so this is the symbol that we use for a power supply. And it always confused me as a student because I think of these little dry cells, battery type things that you buy, in which the small end is positive and the great big back end is negative. That's exactly backwards of how the symbol is designed. Symbol has the long end is positive and the short end is negative. So this is our basic power supply. Okay, you can think of it as like a battery here, but it's really technically considered a power supply. The symbol actually comes from a voltaic pile, in which Alessandro Volta realized if you stack some metal with wet paper between, that the higher you stack it, then the more likely you are to get current going through something. Okay, the current goes through is a resistor. The symbol is R. Okay, so that's a resistor. Okay, and then the voltaic pile, the bigger you pile it, the bigger the voltage. Now they really had no idea what all that meant. They just knew the bigger the pile, the bigger the voltage, and the bigger the voltage, the bigger the current, and it was proportionate to this the property called resistance going through. And so this gave rise to what we call Ohm's law. We'll actually be covering Ohm's law later on in the book, but I wanted to introduce the idea right now. Because if you were to take a power supply here and connect it to a capacitor, and the symbol for a capacitor in a circuit is these parallel plates right there. So that's a capacitor. Okay, now obviously that symbol in an electrical circuit suggests that what we have here is parallel plates. Okay, now your book also introduces another symbol in electrical circuits, and that is a switch. So we have a switch right here, okay, and so as the symbol indicates, you can close the switch or open the switch. If you open the switch, it disconnects everything from the circuit. If you close the switch, then that becomes a wire right there, and then current can flow. Okay, so when we talk about putting a capacitor into a circuit, right there. So this has some voltage V0. Okay, now when the switch is open like this, there's actually no connection here at all to the capacitor, and therefore there's no electric charge in the capacitor. Okay, if you close the switch, then this is the positive side here, that's the negative side, so electrons go spewing out here and land there, and then electrons get pulled on here, you have lack of electrons there, and now we have electric charge on the capacitor. And then the voltage on the capacitor is going to keep going until everything here, this is all a conductor. It's a wire, so this is all a conductor. We know that conductors are equipotentials. If there's a potential difference, then there's going to be an electric field there, and so current will flow until all of the conductor is the same voltage. So that means that if you were to take a voltmeter or a device that measures voltage, this voltage would equal the other voltage that we supplied over there. Okay, so that's how you connect a capacitor into a circuit.